you evaluate two types of vibration characteristics. It's vibration frequencies. Let's talk for the sake of simplicity about linear situation. It's vibration frequencies and coordinate function, so the so-called modes of vibrations. And before we continue, let me simply show you, explain to you what I have in mind. Let's say in the very simple situation, we have a beam simply supported, and let's say it could be a printed circuit board. And the entire system is dropped on a hard concrete floor. After it hits the floor, it will start vibrate, and it will go back. And this will be the first mode, the lowest mode of vibration, which is characterized by this coordinate function, which will be like a cosine or sine, depending where the origin will be. It will be also, if it's a symmetric impact, the mode of vibration of that type will not materialize as the second mode, but the third mode of vibration will, and this will be a different coordinate function. So this coordinate function is for the first mode of vibration. This is for the third mode of vibration. As I mentioned, the second mode that will go like this simply will not be triggered because the impact in this situation that I described will be symmetric. Although, by the way, some time ago, a minute ago, I indicated that if we drop a cell phone, it can go this way. And in this case, yes, the second mode and all the upper modes will also be triggered. So the frequencies that correspond to these modes, 1, 3, 5, and so on, will be, of course, the lowest will be the first will be the lowest, it will be the highest and higher and higher, and the corresponding coordinate functions, it's this coordinate function that corresponds, or response function, you can call them sometimes, that corresponds to the first mode, and this corresponds to the third mode. In nonlinear analyses, typically, usually, we consider that, and I will describe it later, when we use the so-called method of principal coordinates, only in the principal coordinate. And quite often, we assume that the coordinate function is the same regardless of whether we deal with linear or nonlinear vibrations. And the question that I asked myself, or we asked ourselves, with an engineer from Nokia in Brazil. His name is Luciano Arruda, and we published a paper on that in European Journal of Applied Physics, is whether the coordinate function is affected by the membrane forces. In other words, whether we can use the same coordinate function when we do an analysis linear or nonlinear. These situations will become more clear when I'll come to the actual problems that we deal with. Then I will describe some peculiarities, some attributes that have to do with shock protection of portable electronics, and particularly I'll describe how an ideal shock absorber should look like, and how we can isolate vulnerable elements when we want to protect. And I used an example, NCR module. NCR stands for National Cash Register. At that time, when I worked with the people from NCR on this problem, NCR was purchased by AT&T, and we were in the same corporation. And we did, I believe, together a good job in understanding how we can possibly protect portable electronics. You know, the paper is published, and it's, of course, it's often referred in literature, but I am not aware of practical implementations of this approach when you actually use this type of shock protection of portable electronics in actual cell phone devices. Maybe it's too bulky. Then I'll describe a nonlinear cushion with a rigid and soft characteristic nonlinearity, and particularly a special application of nanowires. You know, everyone is involved today and is very interested in nanotechnologies, and it's indeed something that is changing the world and will change the world. And I will also talk about a little bit about nanotechnologies in general, and particularly how by employing nanowires, like even of that type of nano tubes or carbon tubes or whatever it's used for other objectives, how we can use these nanowires as an effective cushion that protects a portable device from drop loading. And I will say simply just a couple of words about photonic systems with an example of fused biconical taper light wave coupler. Although I published quite a number of papers about the dynamics of optical fibers, but in this course I will not cover that because my assumption is that a typical student of this course is not very much interested in optical fibers. And certainly I'll make a couple of concluding remarks. Now, why we are today interested in dynamics of dynamic responses. I have already said a couple of words about that, but it doesn't hurt, and that will be, I do that deliberately, that I will come back from time to time and we'll discuss from a little bit different perspective more or less the same issues. Because typically the way that I, during my long professional life, how I'm learning new things is by reading about the same subject from different books, or by coming back to the same situation and revisiting this, rethinking it from the different points of view. And this is always useful. That's how people learn new things. And that's what I'll do in this course as well, so that after you read it, after you leave it, after you listen to that, you will not have to remember everything, but the most important things you will simply remember. So, motivation, incentive. Why do we need dynamic loading at all? And that's because electronic components and systems often experience dynamic loading. In commercial electronics, dynamic loading can take place during handling or transportation of the equipment. In some cases during mishandling, or if it's not protected adequately, but in the same time, in order to understand how to protect it, we have to understand its dynamic behavior. In military avionics, in military applications, in avionics, in maritime and space, automotive electronics, dynamic loading, whether it's deterministic or random, is expected to occur even during normal operation of the system. And therefore, certainly, and as I mentioned already, in this case, we should consider first separately thermal loading and dynamic loading, and if it's important, also mechanical loading, and then to understand how the system will react to the combined action of these loadings. Important thing that I want to emphasize, that even if a linear approach is used, it doesn't mean that we can simply add up the responses to these different loadings. Some cases it might be possible, but in the majority of cases this approach can be misleading. But at the same time, quite often the system, one mode of loading, whether it's dynamic or thermal or mechanical, dominates, and it's probably we can get away with understanding only this type of loading. And this is true about dynamic loading when it acts on the military, avionics, space, automotive, and so on, different systems during normal operation. Random vibrations, I already mentioned them, are often applied deliberately in addition to or even instead of thermal, cyclic, or mechanical testing as an effective and fast means to detect and weed out infirmalities in the system. For instance, let's even assume that the actual structure, particularly solder joints, joint interconnection, is not supposed, is not expected to encounter a dynamic environment. But today, quite often, we use vibrations, particularly random vibrations, to understand the physics of propagation of fatigue or brittle cracks. And in this case, quite often we combine random loading, random vibrations, and on the shock testers or so-called shakers. And we also, it's important to realize that in many cases, the worst situation for the propagation of cracks and for fatigue cracks becoming brittle cracks is we have a combination of vibrations, including random vibrations and low temperatures. On the other hand, the development of new shock absorbing smart materials and structures is important, and it's important to be able to understand how well these structures can indeed protect or optimize the dynamic response of various components and device to shocks and vibrations. And as a rule, before we do something, before we put something together and we test it, it's always useful. I would say it should be even mandatory, although it doesn't work this way in the real life always, that we do modeling of this behavior. Otherwise, it might take the rest of our lives to really optimize the structure with respect to the particular loading. Now, the necessity to protect portable electronics from shock loading, typically because of accidental drop, resulted in the elevated interest in the development of both theoretical methods and experimental techniques for the prediction of the consequences of an accidental shock, as well as for the adequate shock protection of portable products. And also advanced test vehicles, they're developed and are used and should be used, and they certainly have to understand how they behave with respect to the different kind of dynamic loading. Again, I want to emphasize that certainly it's dynamic loading are drop loading, shock loading, and vibrations. And the responses can be to all these types of loading can be linear or non-linear, and that certainly will affect modeling. So that's why we are interested in the response of electronic and photonic systems to shocks and vibrations. I mentioned many times when I say electronics, I say photonics, although at the same time I said that I will focus very, very a little bit on photonic systems per se, But on the other hand, almost everything, or probably even literally everything, that I will describe as far as the electronic system structures, packages are concerned, is equally applicable to photonics packaging for those who are in this area of engineering. Now, I already indicated the importance of modeling, and now I'll go into greater details about special type of modeling, which is analytical, mathematical modeling based on the methods of mathematical physics, methods of differential equations, and then I will talk about how these methods are interact and related to computer-aided simulations, particularly finite element analysis, and will indicate the role, attributes, challenges, merits, shortcomings, pitfalls, and interaction A between these two types of modeling and B between these two types of modeling on one hand and experimental modeling on the other hand. I want to say, although I will not be talking in detail about experiments, it's beyond the scope of my course, but I want to emphasize the following, probably not very much obvious thing. Some people think that experiments are real life, and modeling, whether it's analytical or computer-aided, is not. It's true that modeling is not real life itself. That's why it's a model. But on the other hand, we shouldn't think that experimentations is real life itself. It's a real life for an experiment, but it's not the real life for necessarily the real life for a actual operation of the device. Of course, if you watch something, what's going on the Milky Way, to an extent that you see that, you can understand that, that's real life. But when we do accelerated life testing, we actually also think how we can model, experimentally, model the real life. And we usually develop a experimental vehicle. We don't call it with the word model, but in effect it is a model. We develop an experimental test vehicle based on our anticipation, on our intuition, our gut feeling of what we want to see. And it's very seldom, although sometimes happen, that you see or detect something different than what you want to model. The point that I want to make that please do not think that the experiment is real life, 100% real life, particularly, of course, the accelerated test is certainly not the real life, it's a distorted real life. But all these three major approaches, I mean analytical modeling, computer-aided / finite element, simulation modeling, and experimentation are the major three whales on which the engineering science is based upon. And it's always desirable that we approach the same problem of interest using all these three whales. Because they have different, certainly they approach the phenomenon or a structure of interest from different points of view. And if the results are in a good agreement, that's an indication that, yes, we can go ahead with certainty. And very often the results are not in good agreement. And each of these approaches has its merits, its shortcomings, and that's why it's always important that we use all of them. However, having said that, in this course I will not discuss experimental approaches, although in some cases I will indicate how modeling was applied to experimental vehicles. And I will talk primarily about the results obtained by analytical modeling, and I will emphasize why this is important and how it can complement computer-aided simulation. Today, of course, the overwhelming majority of researchers and practicing engineers use finite element simulation, and not too many use analytical modeling. And therefore, I want to emphasize in this course that I am not telling you that you should change. Oh, no, you are doing the right thing in general, but I want to emphasize, to indicate where analytical modeling can be extremely useful for people who do primarily finite element modeling. So there is a couple of quotes here that I put them here not just for the sake of to making things more funny, but they have to do, the quotes that I will not use too many quotes in this course, but still the quotes that I will use have, of course, a deep, I would say, meaning. So a theory without experiment is dead. An experiment without a theory is blind. Of course, nothing, as one other physicist put it, nothing could be more practical than a good theory. And that opens your eyes in which direction to go. But on the other hand, it's a challenge. And as Sam Goldwyn from Goldwyn and Myers put it, it's tough to make predictions, especially for the future. Or maybe Yogi Berra said, but it's true. But actually modeling, what it is all about is making predictions for the future. And now I will will remind you, because the majority of you rely heavily on finite element approaches, is we use finite element analysis to evaluate components, packages, structures, systems, when we want to determine the stresses, strains, displacements, deformations. I want to remind you that finite element analysis has become, since the mid-50s, and I remember, I'm old enough to remember when finite element analysis was brought in. The first time, at that time I lived in a different country, Russia, and it was brought into Russia from Germany as a practical tool. It was developed in Stuttgart by a group of avionic engineers chaired by a person whose last name was Argyris. I believe he was a German of Greek descent. And it was the first time, it was the beginning of the 50s, then computer-aided models based on finite element started to be used for avionic structures. Why for avionic? Primarily because these were structures of a very complicated geometry. At the same time, let me tell you this, that the principle of finite element was well known since at least, I would say, the early 30s. And it was a close relative to finite differences, but at that time, the computers were not as powerful as they are today. I also, as far as computers are concerned, that you cannot certainly use finite element today effectively if we wouldn't have computers. But the computers at that time, in the mid-30s, existed. They were not very powerful, were based on vacuum tubes. And something I remember, it was in the late 50s, a computer that was making 100 operations per second was considered a tremendous step forward. Now 100 operations per second will make people laugh. So finite element emerged as owing to two things: to a well-known method, numerical method. One of the numerical methods of implementation of one of the variational approaches in theory of elasticity, and plus computer techniques. The important thing, and maybe not 100% obvious thing that I want to emphasize, that finite element is part of theory of elasticity or theory of plasticity, because finite element is based on the same principles that theory of elasticity or plasticities are based. What it means that all the equations of the mechanics of continuum media should be fulfilled in all the points. Therefore, those people who have a hands-on experience with using finite element, including yours very truly, know that quite often we use finite element, you make the mesh finer and finer and finer, and the stress at the edge of a dissimilar assembly composed of dissimilar materials, the stress goes up and up and up. You end up with a singularity. Why? Not in all the cases, but the overwhelming majority of cases. Why? Because the theory of elasticity requires that all the equations, including an equation of a continuum medium, continuous medium, and that in this are fulfilled everywhere. And, these methods simply do not work in the simplest way. It's true that those, again, people who use finite element, we know that there are finite elements that are based on an analytical approach. Could be also theory of elasticity analytical approach. And then they construct a finite element that actually already considers the singularity, but requires that the equations of theory, well, some equations are fulfilled at a certain very small finite area, segment, rather than in a point. And everything else is fine, works nicely. On the other hand, before I continue, I want to say that many different methods of structural analysis, and I used many of them and published many papers when I used methods of theory of elasticity to evaluate the coefficient of compliance, and then I used methods of structural analysis to come up with the constitutive equations. I want to remind you that the famous Timoshenko paper that was published, I believe, in 1925, the theory of bimetal analysis of bimetal thermostats. It's an engineering paper based on an engineering approach, and later on both approaches were widely used. But let's continue what I want to convey on this view graph is that today's powerful and flexible finite element computer programs enable one to obtain within a reasonable time a solution to almost any stress-strain related problem. Let me tell you this, no question, finite element is very useful and should be used always. However, those people who have familiar very well with finite element knows that it's very easy to obtain a solution using finite element analysis. It will be nice and a colorful picture and everything. It might not be that easy to obtain the solution, and even if, God forbid, you obtain the solution, if you don't have anything to compare it with, how would you know that it's an accurate solution? Yes, there are ways of doing that. You can, if you obtain the same solution with different types of finite elements, or you obtain a similar solution with different meshes, maybe that's what it is. But you still, with the singularity, where the highest interfacial stresses arise, you still don't know what the right stress is. And therefore, as they say, it's quite often it's better to be approximately right than precisely wrong. It may sound like a joke, but sometimes approximate methods in engineering applications might be absolutely acceptable. So what I'm saying that broad applications in computers has, however, by no means made analytical solutions unnecessary or even less important, whether exact, approximate, or asymptotic. And simple analytical relationships have invaluable advantages because of the clarity and compactness of the obtained information and clear indication of the role of various factors affecting the given phenomenon or the behavior of the given system. If you apply methods of rigorous method of theory of elasticity, quite often you end up with equations from which it's hard to understand what affects what, what's responsible for what, and you have to use a computer to computerize this equation, to have to use a computer in order to simply interpret what these equations do. It's still useful, certainly, it's still useful to do this and computerize these equations, and independently also, it will also be theory of elasticity, do finite element analysis, but it's also very useful if you use a simple, approximate, but physically meaningful analytical solution. My philosophy is that if an equation, it's a joke, don't take me seriously, if an equation is longer than 3 inches, it's most likely wrong. And also another funny thing, they say that, of course, the best short, brief equation, which is very meaningful, is a famous E is equal mc squared. And again, don't take me literally, so if you want to change the energy, you better change the speed of light, because it's entered squared rather than a mass. Another thing, also a joke, is even it was not easy, even for Einstein, to come up with such an equation. And people say he tried first E was equal ma squared, it didn't work. Then he tried mb squared, it didn't work. When it came to mc squared, he felt it was just right. But now, to be serious, I want to say that if you can take from Timoshenko, if you can take from any other book, if you take one of the equations that I derived, you can clearly, in the majority of cases, see what affects what and what's responsible for what. And although these equations, these results are not 100% accurate, but they're accurate enough for many applications, and they are very helpful, not instead of, but in addition to finite element analyses. In some cases, maybe even instead of, but usually I would say I do both. And for instance, I use analytical modeling to come up with nice, simple, straightforward pre-processing models. And then what I do, I put together a pre-processing model, then I simplify this model to a situation when analytical solution is possible or available, and then I compare the results. If the results are in good agreement, and again, I want to emphasize the results were obtained based on different approaches, then if the results are in good agreement, it gives me confidence that I can expand the simplest model, pre-processing model, for more complicated situation where I simply cannot obtain the solution using analytical modeling. So it helps. At the same time, there are some paradoxical situations, and I'll talk about them a little later, when analytical modeling sheds a lot of light, provides very useful insight of a physical nature of a particular, even paradoxical phenomenon, where neither experiment nor finite element can explain, because simply what is simulation, what is finite element, is expanded, it's a simulated experiment, where each time you have to solve this problem again from the very beginning. And if the problem, if the results depends on more than 2 variables, you can spend the rest of your life wrestling with an experiment or with a finite element in hope that you'll obtain the meaningful information, what affects what and what's responsible. Oh, I'm sorry, I pushed the wrong button. Let me go back. So why analytical mathematical modeling is important? And to answer this question, I brought in here 3 quotes. You know, another thing is it was a famous French mathematician, Blaise Pascal, you heard his name. He was saying that the subject of mathematics is so serious that you should never lose an opportunity to make it a little entertaining. And I think it's true about everything, particularly such a serious and complicated, complex problem as dynamic response. So that's what I'm trying to follow Blaise Pascal's advice. The famous German physicist Heinrich Hertz, the one who actually was the first who indicated that electromagnetic waves can be used for telecommunications, even before Marconi invented the radio. And he said the mathematical formulas have their own life. They are smarter than we, even smarter than their authors, and provide more than what has been put into them. Well, it's not exactly right. Based on my own experience, they cannot provide more than what has been put into them. But what they actually do is how you derive these formulas. I'll not go into the details. The course is not about that, but I'll just share my experience, and I published dozens, hundreds of papers where I applied analytical modeling to different areas of engineering, is this. Typically, you put as a fundamental of a model some experimentally established or intuitively obvious facts. Again, bringing as an example the well-known theory of relativity, and none of us is even remotely as great as Einstein was, but we want to learn from the geniuses, is what Einstein did. He did first, the principle of inertia was confirmed experimentally and intuitively was correct, but of course the second law of Newton also was proven, that the force can be determined as a product of the mass and the acceleration, and that's how the mass was actually introduced into the physics as a ratio of the force to the acceleration that this force produces. But another thing is how the speeds are added to each other. That's an absolute speed should be obtained as a sum of the relative speed and the speed with respect to a ground or particular coordinate. And we know if we climb along the escalator, our speed can be and should be obtained as a sum of the speed with respect to the escalator and the speed of escalator with respect to the ground. But in this case, there is no limit to our absolute speed. But it turned out that this intuition lets us down, and the speed of light is independent of the system. That was absolutely counterintuitive thing, but it was an experimental fact, and it was put into the model. And that was what the fundamentals of theory of relativity. What I want to say that, of course, the things that little people like myself deal with are not of the same caliber, but also we put into the model some intuitively more or less obvious or well-established things. And then when we develop the model, we obtain the result, we form an equation, we solve the equation, then we see what affects what and what's responsible for what. So it's not that the equation provides more than we put into them, but the equation provides something that was not unclear to what extent it's important. Of course, people probably knew that the speed of light affects the energy, but it was c squared, that wasn't obvious. And that's approximately true about any analytical model. Now, a famous Russian naval architect and applied mathematician, Alexei Krylov, said the mathematics to an engineer is a means, a tool, which is similar to a caliper chisels, hammer, file to a craftsman or a yardstick, hatchet and a saw to a carpenter. And that's certainly important for those who do analytical models. Famous Timoshenko's books are good illustrations to what is said here. And the famous quote of Albert Einstein, "The theory should be as simple as possible, but not one bit simpler." In other words, in the theory, you want to consider the most important things, not to pile up nonlinearities, to pile up numerous relevant or maybe irrelevant factors that may or may not be important for a particular phenomenon. So again, intuition, feeling what affects what and what's responsible for what comes first. And everything, these things that also intuitively are not that important shouldn't be considered. And these models work for many, many, many things up until some experiments or some evidence or maybe other more complicated models show that this model is not adequate for a particular application. Again, the famous example is Newton theory is still good, it will be good for many years to come for situations when we deal with speeds which are much lower than speed of light and for masses which are much larger than masses of elementary particles or maybe smaller than some masses of some stars. Analytical modeling can be helpful in creating the preprocessing finite element model. I already mentioned that. It's easy to obtain a solution based on the finite element software, but it might not be that easy to obtain the right solution. And using analytical modeling in addition to the finite element and using analytical modeling to improve the finite element simulation is very helpful. This particularly true implication to optoelectronics and photonics, where high accuracy is particularly important. I want to say just a couple of words about that. In microelectronics, as a rule, the accuracy that finite element can provide is sufficient. A split of a micron does make a tremendous difference. But it's different in photonics. A split of a micron in alignment of two optical fibers on a fiber in a laser, a split of a micron can affect dramatically the coupling efficiency and make a difference between a functional device or a failed device. And therefore, if you want to use finite element analysis, of course, the accuracy of much better than a split of a micron is important, probably at the level of nano. But it doesn't happen often, and based on my own experience, you change the mesh, you change the type of finite element, and you are way off 2, 3, 4 microns. And with analytical modeling, you don't have this problem. The result can be as accurate as possible. Special attention should be paid and special effort should be taken to make the existing finite element programs accurate enough to be suitable for the evaluation of the thermomechanical displacements in optoelectronics and the photonic systems for the reasons that I've just explained. Also, the analytical models, I mentioned that a couple of minutes ago, are able to explain some paradoxical situations that people were not able to explain based on experimental modeling, on experiments or finite element modeling. And I'll bring several examples based on my own experience that I dealt with, and of course the results are published. First, why do the interfacial stresses in bimetal thermostats concentrate at the ends? So I In this course, I will not go into the details. I explained that in my previous course, but it was not obvious, although intuitively people felt that. But the most important thing is this. Will the thermal-induced stresses in a bimaterial assembly will go up and up and up and up and up when you will keep increasing the size of the assembly? And the intuition many years ago was saying probably that will be the case, but a simple model indicated that it will not, if the situation is bad enough, it will not get worse if you increase the size of the model. By the way, that couldn't be, there were excellent publications based on theory of elasticity where they indicated the stress concentration, the corners, the level of stresses, the different levels of singularities and that and this, but they did not address, maybe didn't try to address, didn't address this situation, and this situation was explained, how it happens, why it happened, and what is the effect of such stress saturation based on a simple analytical model. The other, I'll skip it, could compliant external leads reduce the strength of a surface-mounted device? It was also a situation when people, it was about probably 20 years ago, when only hybrid integrated circuits were people started to use them. And we introduced compliant electrical external leads to make the life of the surface device easier. And let me explain what it was. Let's say this is a printed circuit board. This is the hybrid integrated circuit, and it was attached to the printed circuit boards by compliant external leads, in hope that if this board will be subjected to bending moments, the printed circuit board will bend, but this bending will not be transmitted owing to the compliant leads, will not be transmitted to the integrated circuit. And it worked exactly the way that we thought. However, for some compliances of these leads, of course, if you make the leads more compliant, the bending moment at failure of the Higg should go up. And it worked pretty much in many cases, but not in all the cases. There were some situations, some compliances of the leads for some printed circuit boards, and for some length